Antoine Caradot. Antoine Caradot. Yeah?
Yes, that's right.
Thank you. The School of Mathematics and Statistics, Henan University, China. The title of talk is The Yoneda Algebra of Complete Intersection. Correct?
Yes, exactly.
Share your screen, please, but stop once. Oh. Yeah.
Okay, can you see the screen?
Yes. Everything is good. Good luck.
Okay, thank you. So thank you for the introduction, and thank you to the organizer for the opportunity to speak to you today. So I will present some results on the Yoneda algebra of a complete intersection ring, and also some results in the non-complete intersection case. So this is an ongoing joint work with Tripo Zhang from Shanghai Jiao Tong University and Zhongju Lin from Kansas State University. So first, a brief outline of the talk. I will give some motivation on why we are interested in studying this object and why the results have some pertinence. Then I will give some background on the construction we are going to use for the Yoneda algebra. Then the third part, which will going to be the main one, will be on the results about the finite generation and the presentation of this algebra when the ring we start with is a complete intersection. And finally, I will give some results we have obtained when the ring is not a complete intersection. So for the motivation, when you define the space we are going to look at, you start with some ring R and some R module. And you can define this Yoneda algebra, which is sometimes called also the X algebra. And it's a set of equivalence classes of exact sequence of R module, which starts and ends at your module M. And a way to construct this algebra is to look at the cohomology of a cochain complex, which is obtained in this way. So you take the Hom space of the morphism starting from a projective resolution of your module M, and it goes to the module M. So this will be independent of your projective resolution, and the space you obtain will be the algebra we consider. So this, with the way it's constructed, it will contain both information on the module M itself and also on the ring you started with. So this is one of the motivation. And I mentioned that we are going to look at some finite generation of this algebra. So why are we interested in that? Is because it was motivated from ideas we had in algebraic geometry. Because if you work with some finitely generated algebra, you can see it as some ring of function of an affine variety in some finite dimensional space. And if you then want to work with local rings and everything is finitely generated, you can think of it as some ring of function for a scheme of affine type. And this will help you have interesting results on your scheme. So this was one of the motivation for the study of this subject. So for the definition of the algebra, so as I mentioned, you start with some ring R and some R module M. And the space we consider, this X space, so it will be a graded vector space. And the part of degree n is the space of, so it's a set of equivalence classes. I won't go into detail on how you define those classes, but it's a set of equivalence classes of the n-fold exact sequences of R module which start and end at M. So for example, X1 will be the set of short exact sequences where you start at M and you end at M. So there is a way to define a sum on those set of equivalences, and you have a way to define also a product, so which just the splicing of the exact sequences. So if you want to splice two exact sequences, you take the last map that is surjective on M, and you compose with the first map of the other exact sequence that is injective. And this composition gives you a new exact sequence, which is the product. So this is usually called the Yoneda product. And so that's why we call it a Yoneda algebra. So one way to obtain explicitly this algebra, as I mentioned, is to look at the cohomology of the home space from a projective resolution to M. So this raises a question as to how, if you want to do some explicit computation on this algebra, you need to obtain some explicit characterization of this projective resolution. Because the result doesn't depend on which projective resolution you choose, if you are able to find one that you can compute, then you can carry on the construction. So the goal here is to give you an example of one particular construction that we are going to use later on. So this construction is due to Tate, and it's a recursive construction. So you start with this x0. So you look at it as a complex where epsilon is just the surjection from your module your ring R to your module. And R is seen as degree 0. So you have the positive degrees on the left, and you have the on the right, you can see it at just the negative part. So the idea is we are going to do what Tate called adjoint variables. So we kind of defined elements capital T1, capital Tn. Each of these corresponds to generators T1, Tn of the kernel of your epsilon. And then we define a DG algebra, which will be called X1. So it will be an R algebra where the degree of Ti is 1. The derivative of capital Ti will be small ti. And the commutation rule is you impose a strictly graded commutativity, where R is going to be, of course, of degree 0. So this, as it is a DG algebra, you can think it as a complex, which is graded by the degree, so degree 1 for Ti and degree 0 for R. And if you look at the homology of this complex, you can check that the H0 of this X1 is going to be isomorphic to your module N. But we still don't have the H1, H2, and so on can be quite complicated. So the idea is to modify, to change the construction so that we can basically cancel out each step 1 degree of homology. So then you consider the 1 cycles in your X1, whose homology classes will generate your degree 1 homology in X1. And then you adjoin variables of degree 2. So they are going to be the SI, whose derivative will be the 1 cycles you started with. But now, because the SI have even degree, we don't want strictly graded commutativity. We want some divided power structures. So if you work with something of characteristic 0, then you can just take polynomials with the SI. But if you have some more, for example, prime characteristic base ring, then you will need some divided power structure. So if you do this construction for X2, you can check that the H0 didn't change, it's still M, but you have managed to cancel the H1. And then you keep on doing this construction. So you will define an X3 by adjoining variables of degree 3, and it will cancel the H2 and so on. And so if you take the union of the whole construction, so basically you take the limits construction, you will obtain a free resolution of your R module M. So this is the work of Tate, and this is the starting point of the construction we are going to do. So we will denote this object as the TRM. And so it's a DG algebra. It is strictly graded commutative. And the even power will have some divided power structure. So the question I want to raise is if this construction is obtained after finitely many steps, because when you add your variables, you don't really know what happens when for the homology degree higher than the variables you add. So it might be exact, it might not be exact. But assuming that after finitely many variables, your whole complex is exact and you obtain your resolution, what can you say about the Yoneda algebra and your ring R? So the setup we are going to consider is to answer this question is the following. So you take K, a field of any characteristic, and you take R, some finitely generated commutative algebra, where the Tate's resolution is obtained after adjoining variables x1 to xn, where we denote the degree as ascending, and we look only at the trivial module. So the rest, so M I gave before, here will be until the end the trivial module for your ring R. One more important assumption we are going to impose is that the resolution is the so-called minimal resolution of your module. So a consequence of that is that the complex hom, the derivative on this complex is already zero. So you don't need to take the cohomology because the cohomology will be the same as the existing complex. So this is the second condition we impose, that we have a minimal resolution. So in this case, what can we say about the Yoneda algebra? So to fix some notation to be able to state the result, we define this set X to be the set of homogeneous generator of the resolution, so the set of the variables we've added by Tate's construction. And a way to characterize the basis of this resolution as an R module is given through this set B. So it's the set of function of maps from X to N, such that the image of X is 0 or 1 if the degree of X is odd. So you will see the reason for the definition in a second. You can decompose this set B as the union of the Bn, where the Bn will be defined like this. So notice that this f of x to the power of x, it looks like the degree of some weighted polynomial, and it's exactly the case. So the elements in the basis of the resolution corresponding to such a map f will be written like this, so x to the power of f. And notice that here we have the x1, xn in ascending power, so it will always be in this order, the smallest order on the left and the highest order on the right. And here we have divided power structure coming from Tate's construction. So if you notice as this, it is exactly the degree of this, this monomial. And one more notation we need is we need to define an element in the dual of this resolution, which will correspond to an element in the Yoneda algebra. So we will write it as x star to the f, where again we have an ascending order. The x star, xi star are the dual of the xi inside your Yoneda algebra. Because remember, we have imposed that the resolution is minimal. So the Yoneda algebra is the dual of the Tate's resolution. And notice here, the divided power have disappeared. So it's just a regular multiplication. So yes, one more important point is that the product we have here inside the Tate's resolution is the one we defined in the previous slide, where the rules are defined depending on the degree. Here, the product is the Yoneda product. So it corresponds to this splicing of exact sequences. So this defines the notation and how we are going to express the next result. So if you start with the setup we had before, so some finitely generated algebra where Tate's resolution is of the trivial module is obtained after finitely many steps and is minimal, then this Yoneda algebra of the trivial module is going to be finitely generated by the dual of the variables we've adjoined in Tate's resolution. But this doesn't give yet information on the multiplication and the rules for the commutativity of those x star. We know the commutativity in this space here, but we still don't know it for this space here. But what we can say is that any element of degree n inside the Yoneda algebra can be expressed as a linear combination of elements of the form x star f, for f corresponding to some degree n. So this doesn't yet tell you how to do the commutativity of the x I star, but what it tells you is that you can always kind of reorder any monomial you start to make it as a linear combination of ordered monomial. So you won't have, for example, some kind of free structure where you cannot do some commutativity. You can always reshuffle your monomials. Yeah. And a consequence of this is that because of this reordering, we can show that the Gelfand-Kirillov dimension of this Yoneda algebra will be at most n. And so in particular, it will be a finite Gelfand-Kirillov dimension. And this will have important implications because using this fact and some results of Gulliksen, we can show that the localization of the ring R at the maximal ideal M corresponding to the trivial module is a complete intersection. So a complete intersection ring. So with this, we have, we started with some Tate resolution obtained after finitely many steps, then it implies that the localization of R is a complete intersection. But we can do something in the other direction. Namely, Tate already proved that if you start with R being a complete intersection ring, plus some other assumptions, technical assumption on the relations, then you can find some Tate resolution whose construction stops after adjoining variables of degree 2. So you don't need to go beyond 2. After degree 2, everything is already exact. And we can also check in Tate's construction that this resolution is going to be minimal if the relations, the polynomial relations in R, are at least of polynomial degree 2. So what I mean by polynomial degree is that the sum of the powers is going to be at least 2. We don't care about the degree of the variable, just the sum of the powers. So by taking all this into account and regrouping everything, then if we start with some ring R that is some algebra R, that is finitely generated and the relation of polynomial degree at least 2, then we have an equivalence between the Tate resolution of the trivial module being both minimal and obtained after finitely many steps, and R or its localization being a complete intersection. So if you start with something that is already local at the beginning, then it's a complete equivalence. Otherwise, it's up to the localization of R. And in this case, if one of those two sides is verified, then you can basically always improve your Tate resolution by finding one that stops after degree 2. So if you find one that stops after degree, let's say 5, then it means that you can do better and you can find one that goes to 2. So this is the, let's say, the best case scenario. So this gives us information on the relation on the finite generation of Tate's resolution and the complete intersection nature of the ring R, and also the finite generation of the Yoneda algebra itself. But I mentioned that I also want some result on the presentation of this Yoneda algebra. So this is the purpose of this result. So we need to define some notations because the result will depend on the presentation of the ring R. So you assume you start with some finitely generated complete intersection ring, so given by this quotient. So here, so C1, Ck is going to be a regular sequence inside this ring. And then the trivial module is given by the quotient of R by the image of the ideal generated by your variables. So an important assumption we start with is that the relations are all in the square of this maximal ideal. So you have no variables of degree 1 monomial of degree 0 or 1 inside your relation. Everything is at least of degree 2. So starting from this setup, we can show that the Yoneda algebra is given as a quotient of a tensor product, where you have on one side symmetric polynomial in k variables, so k is the number of relations. On the right side, you have a free algebra in n variables, where n is the number of variables you started with. The degree of, so it's going to be, of course, a graded algebra with alpha being degree 1, beta being degree 2. And the ideal is generated by these relations. So here you have basically the supercommutator between the alphas. And this, here you have the square of your alpha. And the coefficients that appear here are given by the relations in your ring. So basically, your relation, the part of degree 2 in your relation, you look at the coefficients of xi as xj, and you call this npij. And so these coefficients will basically control the supercommutator of your alphas. So this gives you a presentation of your algebra depending on the presentation of the ring you started with. And you can then look that if you want to impose your Yoneda algebra to be strictly graded commutative, then it will be true if and only if your supercommutator here is 0. So it means that all these coefficients need to be 0. And so it means that all the relations have no part of degree 2, no monomial of degree 2, so only of degree 3. And in this case, your Yoneda algebra, you will be strictly a tensor product between a symmetric part corresponding of degree 2, and so your even degree, and an exterior algebra part given by your variables of degree 1. So this gives you an idea of what happens in the complete intersection case. You have your case resolution that's obtained after finitely many steps. Your Yoneda algebra is finitely generated, and you can find a presentation of your Yoneda algebra depending on the presentation of your ring R. The problem is that if you start with any algebra, it might not be a complete intersection. Usually you have more chance of it not being complete intersection than being one. So what happens? What information can we find in the case of a non-complete intersection? So the issue we encounter is that if it's not complete intersection, then we know that the resolution, if we want it to be minimal, cannot be obtained after adjoining finitely many variables. So it means that if you want a resolution in this way, you will need to add infinitely many variables. And so if you want to do some explicit computation, it becomes tricky. So the solution to this problem is to approximate your ring R by your well-chosen ring R tilde, which will be a complete intersection ring, and then use the previous result on R tilde to do some computation, and then extract information on R. So to fix the notation on the R, again, we write it as a quotient of a polynomial ring. We impose the relations to be homogeneous polynomials and homogeneous polynomial of degree at least 2. And the final important condition is that if you take any relation, it cannot be obtained as a combination of the other relations with coefficients in your polynomial. So basically, you have no redundancy in the relations of your in your ideal of relation. If you remove one of the relation, the ideal will be different. So it's basically the minimal generator of your ideal. So then you take all those relations and you can rename them so that you find the longest regular sequence among all your sequences. So you call it C1 to CR. And then you define the ring R tilde by adding some variables to the ring you started with. So you add K minus R variables. So this K minus R, where you don't change the first R relations, your regular sequence, sorry. but then you add the square of the new variables you've added to all the subsequent relations. And so this gives you a new well-defined ring, and you can check that this R tilde is going to be a complete intersection ring. And of course, you have a natural morphism from R tilde to R by just sending a variable to itself if the index, is smaller than n, or 0 if it's bigger than n. So the strategy we are going to implement is, first, we are going to induce a morphism from the Yoneda algebra of R to the Yoneda algebra of R tilde, where here the trivial module C is given as such as an R module, and it's also going to be an R tilde module through this morphism by the composition. Then we can compute the Yoneda algebra of R tilde because R tilde is a complete intersection. So we have a full presentation of this algebra. And then we can determine the image of this morphism pi char. And so if we do that, we can obtain an explicit description of the quotient of the Yoneda algebra. So we still use the same notation. So CP, the part of degree 2, is going to be this coefficient. So remember, CP is homogeneous. So either everything is of degree 2 or there is no part of degree 2. So if you start with an algebra that has this, the previous properties that we explained, then there is an ideal so I, such that the quotient of the Yoneda algebra of R by I is given by this quotient. So this quotient is basically the presentation of the Yoneda algebra we would want if R was a complete intersection. So notice it's exactly the same relation. But because R is not a complete intersection, it will have way more generators coming from the new variables. And so this is just the, let's say, a good approximation of the non-complete intersection case. And in particular, if your homogeneous relations are all of degree 3 or more, then all those coefficients npij and npii are going to be 0, and so you obtain a strictly graded commutative quotient of the Yoneda algebra. And one interesting consequence of this this result is that if you start with an algebra as defined here, then this gives you a quotient, and you know that the Gelfand-Kirillov dimension of a quotient has to be smaller or equal to the Gelfand-Kirillov dimension of the one you started with. And so we can compute that the Gelfand-Kirillov dimension of this quotient is going to be K. And so direct consequence is that this Gelfand-Kirillov dimension of the Yoneda algebra in the non-complete intersection case is at least K. So if R was a complete intersection, it would be K, it would be the ideal case. But if it's non-complete intersection, it will be, it's at least K. So basically you can verify that the less complete intersection you are, so the more variables you need to add to your construction, the further away you are going to get to this ideal case of Gelfand-Kirillov dimension K. So this is kind of a way to see how far you are from the ideal case of a complete intersection. And thank you for your attention. I will stop here.